Okay, so I need to change the plan for the extent references. So I'm going to kind of quickly summarize the problems that I'm trying to solve. Oops, that is not the right thing. So problems. All right, this is specifically when we update shared references on metadata. So currently we look up extent ref count and flags, and then we the delayed ref explosion, which is so let's say delayed ref explosion. So these are two big problems, right? So two of the main problems. So this one right here is whenever we cow a shared block, we need to look up its extent count because we need to know if we are if we're still shared, like if the, so let's say, we have like block and block. Oh, thank you for that. So these guys all point at the same thing. So if we cow down from here, if this is the owner, so say, owner, the original owner, if we cows down, it's really simple. It needs to count and see if there's another reference. If there is, we do the full back ref dance. But if this wasn't here, then we wouldn't do the full back ref dance. We would just delete this guy. So we have to so we cow down to here, we see that this guy is shared. We then need to look up this byte number in the extent tree to see if it's referenced or not. And if it is, we do a variety of things. So like for every shared block, there is a lookup in the extent tree. And this happens during cow. So like I search down to an inode or whatever for every block that's shared on during the whole path. We then have to do like a separate lookup in the extent tree to see if we need to do this dance. So this kind of sucks, right? So we're like incurring an extent tree read for every block on the way down, every shared block that we run into on the way down. Clearly this gets better as like after the snapshot there's the first guy is cowed right away, right? But like the root pointers point to a bunch of nodes, right? So like 200 nodes. So there's like 200 possibilities plus as it every level down it explodes. All right, so this sucks. A lookup in the tree, in the extent tree for every shared block. The second one is the delayed ref explosion. This is the biggest thing that I hate, right? So again, let's play this out kind of as it actually happens, right? And this is kind of like a oversimplification just because I can't draw. I only have so much space, right? Okay. So let's change the color to that. So we're going to cow down to this block right here. Oh, that was pretty. Anyway, so we're going to cow down to there, down to this guy. At this level, we cow and we create a new block. Now, these guys are not touched. These ones over here. This guy is, but these guys are not touched. However, when we did the snapshot, we only pushed our reference to this guy. So this guy has multiple references, the two roots. But these guys all have one reference. So in order to know that this guy and this guy are now shared, because what we've done here is we've created a new block on this side. So this guy is the new one. So now we have to like push down our reference to these blocks, and this one too, of course. So this doesn't look so bad here, but in reality, like on a 16K block, this thing points at like 200 or more than that, like 400 blocks, right? So we cow a shared block, and now we have to push 400 reference updates to the into the extent tree for all these blocks, and we have to do this at every level. So like we'll do like 400 here, and then we'll do 400 here, and then we get down here at the leaves. We only have to do it for data. So like, and file extents are like super fucking fat. So you're looking at maybe like worst case, it's something like 150 reference delayed ref pushes. So anyway, like in this particular case, like where we got 1, 2, 3, so like let's say 2, so like 800 plus 200, so 1,000 delayed refs. So this is 1,000 objects in the extent tree that have to be updated. Actually, 1,000 objects have to be added. This sucks, right? Clearly, there's like the cost hurts up front, but it kind of goes down because like every time we cow this guy, we don't have to like re-push everything. It's only in the shared. Only when we're breaking the shared. The sharing is that this sucks. Okay. And then sort of like minor things, minor problems. So minor backref lookup. Man, I cannot spell. Lookup sucks. So the way we get around needing to update, so like for example, we cow this guy, right? And then we cow, but we don't, and we cow this guy, and we cow this guy, but we don't cow this guy, these guys. And the way we do backrefs currently is when we created all of these blocks, we just recorded that they belong to this owner. They belong to root, ID, whatever. So we don't actually know who their parents are, unless you do full backref, but that's another story. So when we want to do the backref walk for this block right here, for example, with the way the tree looks currently, it'll only have a reference saying that it's owned by this block, right? So what we have to do is we have to search down to this block, and then we have to find all of the blocks that we had here, and then we have to do a backref lookup for every single one of them. So we search down from this tree down to this block and say, okay, this is its parent. So let's go find this guy. We search down and we add any blocks that were in its path before. So this was already in the path, so we won't add it. So we've done this search and go, okay. And now we look at this block, right? At this point, it has two references: the original guy and the snapshot. And at that point, we know that like, okay, this is where it is. But like, we have to search all the way down here, and then search from here, and like, it gets super messy. So like, say we wanted to go from this guy, right? So we search down, because we have the original owner, we search down here. And then we have to like walk back up. So we walk up and we see this guy, and we see this guy, and then we go to there, and then we go to there. But there's a lot of searching that goes into this. So this is kind of sucky, right? And this is because children don't point at their parents. Because if children did point at their parents, anytime we did this cow, we'd have to like go and update all these guys, which is kind of terrible, right? Right. So that's the problems with the current system. This is what we're trying to change. Okay. So, Lord, drop trees. My goodness. So this was my original idea. So we would have a snapshot tree to track. Lord. Track relationships between roots, and then we have a drop tree to track who no longer references us. So, what does this mean? This means that we would now, instead of, oh Lord, whatever. Instead of doing this thing where we have to push references around for everything, we would simply never push references for anything. And then we would encode a snapshot ID. So we would start with a snapshot ID of 0. So these guys would all have 0 for their snapshot ID. And then when we'd take a snapshot, we'd say, okay, in the snapshot tree, we'd say A was snapshotted by B at 1. So this would have its snapshot ID increased to 1. I would say that A referenced B at 1. That way, we could at any point say, okay, this block right here, oops, let's use the pointer. Say that this block, okay, has a snapshot ID of 0. Let me look up in the snapshot tree and find everybody that everybody that has a reference to A at snapshot ID 0 or larger. So, or 1 or larger. So like if I snapshotted this multiple times, like there would be like a C here with like an ID of 2 or whatever. So like you know that it's possible, right? And then what you would do is at cow time, say we go down this way, we would say, okay, this is snapshot ID 0. Or yeah, snapshot ID 0. I'm snapshot ID 1. I know I need to break it. So I would cow a new block, and then I would, insert a drop item that says, a drop, okay, so call this block, call this block 2, a drop 2 at snap ID 1. And then what you could do here is that what you could do with this is then say, like, if we take a snapshot at C, what the hell? C, it's like at, A, C at 2. We could say, okay, we dropped at ID 1. So we would, later on, we could look up this guy and say, okay, B was at 1, so it was there, but I have a drop ID at snapshot 2, and so we know that C doesn't reference us because it was done at 2, right? So we can tell that its total count should be 2, and its current count is 1, because it has a drop count of 1, its maximum count is 2, and we're good to go. This sounds great, right? Because at every cow level, all we have to do is insert a drop for the block that we care about. We don't have to do this push down thing. The problems with this are that it gets really fuzzy when we talk about taking snapshots of snapshots. Or even, let's say, just normal snapshots. Say we take 1,000 snapshots. In order to figure out who this guy points to, we have to go into the tree and put together a directed graph of every possible ancestor of A, and then figure out from the drop entries who could be pointing at it. So say there's 0 drops. Pick this guy right here. Say we create A, and we do all this stuff, and we could take 1,000 snapshots. We don't know this guy's theoretical count without going and reading in all of the entries and building this 1,000 entry directed graph, and then getting a full count. That's not that bad, right? Getting a full count isn't that bad. Okay, this is kind of a lot of work, but it's not that big of a deal, because then you're like, oh, okay, well, this guy has like a maximal count of 1,000. We could even like cache it in the tree and say, okay, I checked at this generation and this was the count, so we only have to do it once. And then we just wait for the drop count to equal the maximum count, and we drop it, right? The problem here is Q groups. Q groups cares about, so let's do another one. So Q groups, it cares about, one of these days, cares what am I doing? About shared. This is easy because, snapshot means all referred equal, snapshots, targets, exclusive goes to 0, and then target and source and refer goes to source size, and source just exclusive goes to 0, right? But it cares about many to 1, and it cares about 1 to none. So 1 to none is not that big of a deal, right? That's freeing. When we free, we know, okay, this is the guy that freed it. This is problematic, especially with the drop tree case, because again, we know who theoretically references us. We don't know, we can't find out directly without walking through each one of the guys, each one of the snapshots, and searching down and figuring it out. Well, that's not true. We have the drop entries, right? But again, assume 1,999 drop entries. We still have to build this entire directed graph and then walk through all the drop entries and remove entries from the directed graph until we have the guy that's left over, and then we know that's who it does. This is a relatively expensive operation, CPU intensive operation. And then it has to be done twice with Q groups. It has to be done once when we go from n to 1, and then again when it goes from 1 to 0. Because again, from 1 to 0, we then have to figure out who was pointing at us and who needs their exclusive and referred count to go to 0. This is actually not that hard. We can just kind of keep track of who touched us, but this part is super, super annoying, especially with drop trees. It makes it really complicated. So my plan was to put all this work in the garbage collection tree, but if you're talking about 1,000, 10,000, a million snapshots, and every fucking block has to do this calculation, because they would, we could cache a lot of this. We'd say, okay, blah at 0, but we can't cache this because every block has their own drop count. So we can cache the directed graph, but we can't cache the drop count. So we're having to walk through the drop tree to do this. So potentially every block has a really CPU and possibly disk intensive operation to free it. That's not great. It's essentially unbounded. It's n of number of snapshots. That's not lovely. And this doesn't have that problem, right? So when we free this block or whatever, it's okay, we dropped our reference, its reference count is 1. If this guy drops his reference, its reference count 0, and he can be yeeted. So it's not that big a deal. The n to 1 is still super annoying, and the backref is super annoying, but it's not bad. Also, this stuff is complicated to explain. Let's not discount the drawback of like having to explain how this scheme works to new developers or existing developers for that matter, because reference counting is easy. Magic calculations is hard. All right, so 20 minutes of explanation to get to the new plan. So this is, what are we calling this? Reference objects. Okay, so instead, what we want to do is currently we track reference counts are based on byte number, right? So like we're clearly this is like a block thing, and so we have like a block entry that says, okay, that's indexed on byte number. So okay, this byte number has this reference, right? So this new byte number gets a new reference to the thing, and as we go down, and when we push down, we say, okay, push a reference to the byte number. This means that like there's a lot of churn on the extent tree in general. And it makes it so we have to do the that is drop trees. So this makes it so we have to look up the extent ref count, because we don't encode the reference count into the block itself, because clearly it can change, and we are cow, so we can't modify this after it's been written to disk. So we can't just be like, yo, this is multiple references now. So we have to do this lookup because we're indexed on byte number. Because we do this like, hey, my root has this thing. So like when we cow down, we have this awkward moment. When we cow down, we have this awkward moment where we don't know, like we want to push full back refs to these guys if we still have this reference. But if we don't have this reference, we don't want to push full back ref. We want to just free the block. So like you have to do the read. You have to look it up to know what to do. Okay. So the reference object gets away from this. So instead, what we do is we have our tree, right? My goodness, stop being helpful. Instead, what we do is we don't, before with this, we did the roots, because like I said, if you can't have pointers from the children to the parents, because like the block pointers change. We cow it to this thing. We don't have to like go and update these blocks, right? So like there's no upward pointing. It's all downward. This kind of like screws us in these cases, right? The backref lookup sucks because we have to go down, figure out who's there, and look up, right? And we have to look up the extent count because we just have these implied, what we call them implied references. We have full backref, which is like, hey, this byte number points at me. And then we have implied backref, which is, hey, this root points at me. Full backref is easy, and we only use it for shared blocks because we know this block isn't going away until it's actually fucking freed. But we can't do it normally because, again, this problem, right? We can't just randomly update these guys' and these guys' paths, or like the non-shared case. We don't want to be constantly updating everything to point the new byte number if we cow this guy. Since this tree right here is essentially frozen, we can do this bullshit, right? So what we want to do instead is encode a ref ID into every single block. So every block gets their own unique ref ID. So here's 1, 2, 3, 4, 5, 6, 7. Okay, and instead of doing the byte numbers or the roots for the implied reference, we instead ref count by ref ID. So, for example, block 2 what is wrong with me? Has a ref count of 1, and its ref is 1. Same down here. So like block, or not, so ref ID. So ref ID. This is the wrong thing. I don't know why I did that. Ref ID. And ref ID 7, has a count of 1. Ref is 2. Now, what does this mean? What this means is now we have a pointer all the way up the chain. So this is super nice, right? So how does this work in the normal case? So the normal case is we want to cow this block, right? If it's not shared, we cow the block. It keeps its ref ID of 1. So this, and that way, and then we update its byte number, byte number equals, so this is 0, 1, 2, 3, 4, 5, 6, and we update its byte number to 7, right? So we go and we update the ref ID 1 to say, okay, its byte number is now 7. All right, this is a little bit churny, but again, in the current scheme, anytime we cow, we have to delete this reference, add this reference. And so it's a deletion, which is randomly in the extent tree, and then it's a insertion, which is again randomly in the extent tree because it's indexed on byte number. This way, if we cow down here or whatever, we're like updating 1, and then we're updating 2, and we're updating 7, and like updating them to point at their new byte number. The reference counts don't change. It stays the same. Now, what do we do when we okay, can I copy and paste? This will be fun. Nope, that's not it. That's not it either. Select? Is there a select button? I'm sure there is. Things that I should probably figure out before now. No, that is not it. I swear to God, I've seen Callie do this. There you go. Hey. Fancy. Nope. Copy. Paste. Fancy. All right, anyway. So now let's say we snapshot, right? So now we snapshot. And this gets a new ref ID, 8. Ugh, what the hell? 8. So we have to push down our references, right? So can we fucking not? So again, we're going to push down a reference. So now block 3, reference ID, or ref ID 3 has a ref ID, has a ref count of 2, has a ref ID of 1, has a ref ID of 8. Now, when we cow down, when we are cowing down, again from here, cow down to this way, what we do here is we say, okay, this block right here is shared. We know it's shared because it's the snapshot ID is going to be less than, because I'm keeping snapshot IDs for other reasons. This snapshot ID is less than my current snapshot ID. It is shared. Instead of needing to look up if I'm still referenced, I simply say, okay, I am going to drop this guy. I'm going to drop my reference from this guy, and I'm going to create a new reference ID. So now I have a reference ID of 4. And I'm going to drop my reference ID of 1 from this block, and then I'm going to push down my references to this. Now, oh my goodness. So now, blocks 5 has a reference ID to 3 and a reference ID to 4, and has a reference count of 2. Now I still have to do the delayed refs thing. So the delayed ref explosion still exists, but now I have 0 lookups, essentially 0 knowledge actions. So I have eliminated the lookup into the extent tree to see if this guy is shared or not, because I don't care. I care that I have my ref ID that no longer references this block because I broke the sharing. So I allocated a new reference ID, and the new reference ID gets updated with my new block. I push down all the children. I push down my reference from this guy. This still sucks. Like, we still have the delayed ref explosion. It's still a bummer. But I didn't have to look up anything. Once this guy drops to 0, this will happen in garbage collection. So once this guy is completely freed, his references will be dropped on these blocks later on. And it's like, and that's how okay. Sorry, this is complicated. So we will drop our count here, and if we come down this way, we will drop this count, and we will get new ones, and we'll drop the count for the previous one and push for our current one. So this, like I said, we don't eliminate the push down. Like the push down still has to happen. But we eliminate, so okay, like eliminate extent tree lookup and implied refs. So this is the thing that I was talking about earlier, where finding the back refs is kind of annoying because we basically have to search down to a particular block. And the other thing is, like, you have to know what key is in this block. So not only do you to do the back ref lookup, I'd have to read the code to be sure, but we have to literally read this block to get what its key is. and then search from the owner down to this key. That's how we do it. So we do a read on this block, and then we search, so we read all of these guys, and then we walk up through the extent tree, possibly reading down to intermediate blocks. So it's like, worst case, it's 1, 2, 3 reads plus all the reads that you need to do to actually look up the extent objects. With this case, since we have our parent pointers, we know exactly who the hell is pointing at us, we don't actually have to read this block at all, or these blocks at all. We just say, oh, okay, I want to know all the references for 4. So my references for 4 are 3, or block 4. My references for block 3 and 4 are ref ID 3 and ref ID 4. Okay, read in the extent tree, find me ref ID and ref ID 4 and ref ID 3. Okay, who points at ref ID 4? Who points at ref ID 3? And you can literally just look up in the extent tree without needing to look up this guy. So it saves you a search down the FS tree. You can do it all in the extent tree. And it saves, the implied refs are pretty expensive, right? Because you have to do this guesswork of searching down and looking and searching down and looking. And this way it's we literally go from the bottom up. And most cases, almost all cases, okay, the common case of backref lookup is we only want to see if we're shared. As soon as we find a level that's got multiple references, we're good, right? This is FIE map. FIE map wants to know if we're shared. So we walk up, and we walk up to here, and oh, okay, we've got multiple references. We're good to go. Yeah, same with Q groups, right? Q groups, again, cares, n to 1, and then 1 to 0. So if we're trying to figure out if we've gone to 1, we can be okay, this guy has multiple references, we're done, we don't give a shit. Or this guy has just 1 reference, okay, we need to do the exclusive to non-exclusive, or non-exclusive to exclusive conversion. So yeah, this is the new design. Okay, what does this mean in practical terms? So practical changes. All right. We need to encode the ref ID in header. This is what every block will get a new ref ID. So the header will have the ref ID. We also have to encode the ref ID in the block pointer. So right now the block pointer has byte number and then generation. This will have to have a ref ID here. This is what we'll add, because when we do this push down work here, before we just did it on the byte numbers, right? Because we knew what byte numbers we were pointing at, obviously. Now, since it's based on ref ID, we had to have a way to find the ref IDs without looking at all the children, right? So just how when we change a child, we have to update the block pointer and our parents. We'll have to update the block pointer and our ref ID. This is not hard we are currently update the block pointer for the new byte number anyway, so it's just extra information to encode. But that does mean that we'll hold a third less nodes per a third, right? I don't know, I'd have to do the math. 16K blocks, we're adding 64, we're adding 8 bytes per node pointer. So before we had the 24. Well, we had the key too. So before we were, yeah, because we currently also have the key. So currently it's what? 8, 8. So 8, 16, 32, 60, the 30. Can I please count 24, 32 plus the U8 for the type, so 33 bytes per block pointer. This will make it 40, 33. Can I add, please? 41 bytes. So I don't know what that turns out to be. And the iPad doesn't have a calculator. I forgot about that. That's so annoying. Anyway, there's a loss here, right? We're gonna have slightly more shit. The file extents items will they will store the ref ID. That's not true. It'll be tied to the leaf that does it. So like the file extent items will now no longer have like the roots. They'll have the ref ID of the leaf that contains them. So that's okay. What else is there? I think that's it. So these things are kind of big. Before I added a snapshot ID to the header as well. So like I already grew the header once for this. That was originally for this drop trees, but I still need it for snapshots. Right now, if you take a snapshot, we like have to do it in the transaction commit to make sure that nobody messes with things, because we don't have a good way to tell that, if you snapshot, A and then B, and then you start changing from B, we don't have a good way to say like, okay, this is breaking it, because the generations will match. Or if you go from A again, like we have to do some like kind of weird shit where we like mark the root as like forcing a cow for everything. And so snapshotting is awkward in that we have to do it in the transaction commit, because we can't allow parallel updates while we're doing the creation of the snapshot tree, of the new snapshot. So the snapshot ID solves this problem, because we can say, okay, if the snapshot ID doesn't match, we updated it when we created the snapshot, and therefore we can do snapshot creation whenever. We don't have to do it in a transaction commit. We can do it literally anytime, and it'll always be consistent. So we still need that, but this adds the ref ID to the header, and then the ref ID to the block pointer. From there, because this is such a heavy duty change, before I was just going to use the same format for all trees, because copy on write tree, like cow only trees, like the extent tree, for example, or the free space tree, don't need all of this crap. And we'd rather they be well packed. So what I'm going to do is I'm going to make this basically only for reference counted trees, and then the cow only trees will just still be the same old format, and I won't even have the snapshot ID in them either. So yeah, this is the current plan until we discover some other horrifying consequence to this. I was really hoping to get rid of the delayed ref explosion, because this is kind of problematic. I don't think there's a way around it. I tried to make the drop trees work, but it's too complicated and too nebulous what we do for garbage collection. So I think this is the devil we know. We've been dealing with the delayed ref explosion forever. It's not that big of a deal. It just kind of sucks in theory. But we can at least kill this, and we can make this significantly better. So I think those are valid reasons to continue. Anyway, that's the plan.